Make sure you've completed the retrieval practice on Microsoft Forms before watching the rest of this video. The link to this is found under the retrieval practice section of this assignment on Microsoft Teams. As you watch this video, make notes. This can be in the form of bullet points or a mind map. The learning purpose of this lesson is to be able to explain how technology can mitigate tectonic hazards in order to assess the effectiveness of the technology. In order to achieve this, we are going to do the following. Describe how technology can be used to monitor and protect against tectonic hazards. Explain how technology can reduce the death toll of tectonic hazards. And evaluate how effective the technology is at mitigating these tectonic hazards. As this lesson focuses on mitigation technologies, we need to first understand what is meant by the word mitigate, mitigating, or mitigation. Mitigate comes from the Latin word mitis, meaning less, and ago, meaning make. In other words, mitigate is to make something less. In the case of tectonic hazards such as earthquakes and volcanoes, mitigate means to make the impact of these less, such as lowering the potential death toll. We are going to examine mitigating the impacts of earthquakes first. Earthquakes cannot be reliably predicted in advance, as they do not show any pre-warning signs, unlike volcanoes. However, networks of seismometers and lasers can be used to monitor Earth movements in areas at risk of earthquakes. The information recorded from these are sent to monitoring stations and can give a small, i.e. a few seconds or minutes, but vital amount of warning before a large earthquake occurs. Monitoring stations are linked to early warning systems used in at-risk countries. These are warnings that are communicated to people and control systems when shaking is detected using the internet, text messaging networks, and sirens. This means that people can get under cover, such as under tables, before the shaking starts. The following video shows how an early warning system worked in Japan during the 2011 earthquake. Seismometers detected a 9.1 earthquake off the coast of Japan. This information triggered early warning systems within the country, which are in the form of messages broadcasted on TV stations informing people on how to protect themselves from the earthquake's tremors and resulting tsunami.
おはようございます。6時になりました。NHK ニュースおはよう日本です。
So you can see on the screen that the early warning system has triggered warnings.
強い揺れに警戒してください。緊急地震速報です。強い揺れに警戒してください。
緊急地震速報です。福島県、宮城県、山形県、茨城県、栃木県では強い揺れに警戒してください。テレビの画面は福島県いわき市の現在の様子です。カメラが左右に揺れています。NHK の各放送局からの情報によりますと、先ほど午前6時ごろ、東北地方で揺れを感じました。震源が海底ですと津波の恐れがあります。海岸や川の近くからは離れてください。
So the video ends with the warning given that a tsunami might be happening. This tells people exactly what to do immediately as the earthquake is happening, which could save lives. Volcanic eruptions can be predicted if the volcano is well monitored. Predicting when a volcano is going to erupt gives people time to evacuate. This reduces the numbers of injuries and deaths. Scientists can monitor telltale signs before a volcanic eruption. Remotely operated seismometers, lasers, and other sensors such as infrared cameras can detect indications that an eruption is likely, such as tiny earthquakes, escaping gases, heating under the surface, and changes in the shapes of the volcano, e.g. bulges in the land where magma has built up underneath it. The following 3 videos show how the United States Geological Survey, known as the USGS, monitor volcanoes for signs of a future eruption. The first video looks at changes in the volcano's shape, otherwise known as deformation.
One of the things moving magma tends to do is it tends to deform the surface of the Earth. It tends to cause the surface to bulge upward or to spread apart. One of the instruments we use to measure deformation is a tilt meter. A tilt meter measures very subtle changes in the surface of the Earth as magma accumulates beneath the station or moves upward, for example. Another instrument we use is the Global Positioning System, or GPS. So we put several of them out on the volcano. We record signals from satellites orbiting above the Earth, and we look for movement of one of the stations with respect to the other. As the ground deforms, the volcano changes its shape, those stations move, and that tells us something about what's going on beneath the surface.
Okay, the second video looks at how earthquakes can be warning signs of a volcanic eruption.
Most earthquakes associated with young volcanoes are related to the movement of magma deep beneath the volcano and may indicate that a quiet volcano is becoming active. Although large eruptions are often preceded by several significant earthquakes and many small rock-breaking quakes, there's also a continuous release of seismic energy associated with the underground movement of magma. Volcanic tremor is a seismic vibration caused by the pulsing of pressurized magma and gas and can last for minutes or days. The seismogram is of longer duration and more continuous than rock-breaking earthquakes of the same amplitude. Earthquake swarms recorded by seismometers and the ground deformation monitored by tilt meters help scientists determine the location and depth of moving magma beneath the volcano, which in turn gives scientists information to issue hazard warnings.
Okay, that video actually showed you how scientists can use things like earthquakes to mitigate the impact. Warnings can be given out, people can then move away from these areas and are no longer at risk. The final video in this section looks at how Iceland monitors and predicts volcanic eruptions. This links into your Icelandic volcano case study in regards to how effective Iceland was at mitigating the impacts of the eruption. You should already know that there were no deaths or injuries from the Icelandic volcano in 2010. This was in part due to the absolutely fantastic job that Iceland does at monitoring its volcanoes and making sure that warnings go out as soon as information is received.
Iceland and its volcanic belt has 35 active volcanoes. When just one erupted in 2010, it paralysed European air traffic for a month at a very high cost to airlines. Iceland's volcanoes could erupt at any time, so European scientists are closely monitoring them. They want to better understand what happens before, during and after an eruption.
We need to understand how we live better close to a volcano. Here in Iceland, it's a part of the daily life, and occasionally, once in a while, like in 2010, we have serious consequences for many more people on Earth. And in particular, we want to address how we can mitigate the effects of eruptions that provide threat from long-term transport of ash and gas.
Different techniques have been developed. Scientists from the University of Florence just installed an infrasound device in an Icelandic forest. At the end of the year, there will be 4 infrasound installations throughout the country.
This is the central station which collects all the data and sends it through Wi-Fi. At the moment, this data is received in Florence in Italy, and it's also sent to the Icelandic Meteorological Office in Reykjavik. Today we have to check one of the infrasound sensors.
When an eruption occurs, the pressure wave from the explosion enters the atmosphere. This is what the infrasound arrays will pick up.
We're able, with these infrasound sensors and using the array sort of antenna, to detect pressure variations produced by a volcanic eruption at tens, even hundreds of kilometers. If the pressure is very strong, we can detect it at thousands of kilometers.
But the European Supersite research project's not only about infrasound devices. There's GPS, a strain network, gas sensors, water flow for hydrological chemical dispersion, electrical field sensors, weather radars, and ash fall meters.
In future work, we have many researchers that have been working in Iceland, and now is the time to combine all their expertise to provide maximum and better information on the status of the volcanoes. And then when we have an eruption, about the progress of the eruption and how much volcanic ash is coming out of a volcano, because that is so important for the aviation to understand how we fly safely.
All the data from the different monitoring networks is analysed at IMO, the Icelandic Meteorological Office, which despite its name is a natural hazards monitoring institute. Everything's done in real time, 24/7, to warn civil protection services and air traffic control as early as possible.
To monitor the magma movements, we use the seismic location of earthquakes. The GPS networks show us the deformation of the volcanoes, where they're expanding, contracting, things are moving. We are setting up a database and a data service at IMO. It's the FutureVolc database. And it will enable people to access all this data from all these networks on the ground, and also to find ways to get to data from satellites.
If the Katla volcano, the largest in Iceland, was to erupt, the chaos in the air traffic would be far more important, multiplying the economic losses for Europe. But with these new methods and a better knowledge of volcanic crises, a warning, even a short-term one, is still better than none at all. These new data can prove vital next time.
There could be an eruption in Iceland today, or next week, or next year. It is difficult to give what we call sort of the medium-term warning that says when a volcano will erupt.
Volcanoes are not just monitored before an eruption, they are also monitored during the eruption, which helps authorities respond appropriately. For example, evacuation zones can be extended if the eruption becomes more violent. Ash clouds that can damage aircraft can be tracked using satellite imagery, which means that flights can be diverted or cancelled, so passengers aren't put at risk. Instruments installed on and around the volcano can detect the spreading of ash and poisonous gases, which means authorities can warn people to put on gas masks. Modern building technologies can be used to design buildings that do not collapse in earthquakes or when covered in volcanic ash. This reduces deaths and injuries from falling masonry and reduces the costs of repairs and rebuilding afterwards too. The first building technology we're going to discuss is cross-bracing. This is when walls of buildings are built with two diagonal supports in an X shape, as shown on these images. This helps provide strength and support, preventing the building from twisting in an earthquake. Buildings can also include shock absorbers in its foundations. This allows the building to move side to side as the earthquake happens, and absorbs the shock waves from the earthquake. This means a building is less likely to crack or collapse. Shear walls are another building technology that mitigates the impact. These are thin walls made from concrete with steel bars within them. This helps to reduce rocking movements and to stop concrete walls from cracking and collapsing when shaking. Automatic shutters can be added onto buildings, which come down over the windows when shaking is detected by sensors within the buildings. This stops from shattering, which could cause damage to people below the building. Pipelines, such as for water and gas, can be designed to flex and not break during earthquakes. Buildings can also have sensors, shown on the image on the PowerPoint, which shut off water and gas when it detects shaking. This helps to prevent deaths and damage to properties caused by flooding and fires. The following video goes into more detail on building technology to mitigate tectonic hazards.
More than 1 million people have died in earthquakes in the last 2 decades. Seismic rumbling between the Earth's tectonic plates puts some of the world's most densely populated countries at particular risk. These plate boundaries are most apparent around the Pacific Rim. Frequent earthquakes have led to the region's nickname, the Ring of Fire. Yet for the most part, earthquakes themselves don't pose the greatest risk. Collapsing buildings do. While buildings are generally designed to withstand vertical loads, the weight of their contents and inhabitants, they've not traditionally been built to withstand the side-to-side swaying that a tremor can bring. It's possible to design buildings so they're more resilient to earthquakes, keeping them light and flexible so that they can absorb and distribute the energy of their movement. Start with the roof, which should be the structure's lightest part. In the 1995 Hanshin earthquake in Japan, and the recent quakes in Nepal, much of the damage was among top-heavy tiled roofs. In 2008, a magnitude 8 quake in the Chinese province of Sichuan took more than 80,000 lives, and engineers found tile-clad buildings largely to blame. Using materials that can bend without breaking helps make buildings more shock-absorbent. This building has steel embedded in its frame. It's being put through its paces on what is known as a shake table at the Hyogo Earthquake Engineering Research Center in Japan. Tests like these show how a building's frame is also important. Light walls and partitions and thin concrete floors can help. So can what are called shear walls, a system of panels and braces that effectively channel a side-to-side force downward into the building's foundations. The giant concrete columns at the center of modern skyscrapers do exactly that. There's also a bit of simple physics known to the architects of ancient Japanese pagodas. These were built with a giant central pole called a shinbashira, which acted as a tremendously heavy pendulum. Seismic shuffling of the pagoda's main structure transfers into the gentle swaying of the shinbashira. Since it was built in the early 7th century, the enormous Horyuji Temple in Japan has survived dozens of big quakes. Modern builders have taken note. Taiwan's Taipei 101 and the Citicorp Center in New York use hundreds of tons of concrete or steel to do the same job. All this has the potential to make newer buildings safer. But as much of the infrastructure damage in Nepal has shown, it's also very important to apply this hard-won engineering knowledge and retrofit older buildings as well.
The Economist.
Exit this video now and complete the Word document found under the Output section of this assignment called Student Activity Mitigating Tectonic Hazards.